Recall that organic chemistry is the chemistry of carbon. And what's special about carbon is that it can form stable bonds to itself. So that's different from, for example, oxygen or nitrogen. Carbon can form long chains of stable bonds to itself. So it can form straight chains, it can form chains that have branches, the branches could have branches, they could have rings. There is an infinite variety of different shapes that carbon can make. And it's the relationship between those shapes that end up communicating messages, encoding messages in living things. And that's the reason why organic chemistry, or the chemistry of carbon, is the basis of life. Okay, well, that's very exciting, because you can form an infinite diversity of shapes. But it's also daunting. How do you study that infinite diversity? How can, in 36 weeks, in 2 semesters of organic chemistry, how can you learn about every possible organic molecule? And the way that organic chemistry is organized, the way that you can learn about every possible molecule, is because on all of those different carbon chains, there are groups of atoms that repeat. And no matter what carbon chain they're on, they always behave or function in the same way. Those groups of atoms are called functional groups. So functional groups are groups of atoms that always behave the same way, no matter what carbon chain they're on. And so, if you learn each functional group, and you learn how it behaves, then no matter what carbon chain you see it on, you will know how that compound will behave. So even if you've never seen a carbon chain before, you will recognize the functional groups on it, and you'll say, oh, I know exactly how those functional groups behave, so you'll know how the compound as a whole will behave. So, organic chemistry 2 is really the chemistry of functional groups. In organic chemistry 1, you learn a lot of foundational stuff. You learn stuff that will come back and you will use constantly in organic chemistry 2. But in organic chemistry 2, we're mostly applying all that stuff to understand how these functional groups behave. And the first one we're going to study this semester is a functional group called an alcohol. So an alcohol is an O and an H. It's really a derivative of water. If you imagine having oxygen with 2 hydrogens on it, that's water, right? You replace one of the hydrogens with a carbon chain. Remember that in organic chemistry, a capital R is sort of like an X in math. A capital R means any carbon chain. So if you replace one of the hydrogens in water with a carbon chain, you end up with an alcohol. So these alcohols are going to be derivatives of water. And no matter what chain the OH appears on, whether it is on a 2-carbon chain, as in drinking alcohol, or whether it is on a gigantic chain, as in this molecule over here, this crazy thing, which has this OH at the bottom, wherever the OH is, the OH will always behave the same way. Now this first exercise, exercise 13.1, is going to be introducing us to alcohols by trying to get us to name them. And if you'll remember from Organic Chemistry 1, there are some systematic rules developed by IUPAC. That's the International Union of Pure and Applied Chemistry. IUPAC is really just a club of chemists who love to give names to molecules and decide other things that help everybody. IUPAC has come up with a sort of naming system that helps you to name molecules based on the prefix, the infix, and the suffix of the molecule. Now, for an in-depth discussion of this, if you don't remember this at all, I encourage you to refer to the review playlist, where this is introduced for the first time and gone over in detail and applied first to simple molecules and then built up to more complicated ones. So here in Organic Chemistry 2, we're going to build on that knowledge that we gained from Organic Chemistry 1. And the new thing here, this whole table should just be familiar. You should have this table memorized already. And the new thing is going to be the suffix. Remember, the suffix represents the functional groups. So that's really what we're going to learn new for naming this semester. And the suffix for alcohols is OL. So any alcohol will end in an OL. For example, this drinking alcohol is ethanol. And you'll notice that OL at the end is representing the fact that you have this OH on it. This complicated molecule on the right is cholesterol, and the OL at the end of it is telling you that you have this OH alcohol there that will behave in its unique way. Okay, so alcohols are functional groups, and they're the first functional group that we're going to explore here. We're going to introduce ourselves to them just by naming them, so training our eyes to see them. And this will give us an opportunity to review these rules that we learned in Organic Chemistry 1. Okay, whenever you want to name a molecule, the first thing you want to do is to find the backbone. That's the longest carbon chain you can find without going backwards or lifting up your pencil. Now you want to make sure that the functional group is on the backbone. So here we want to make sure that this OH, this alcohol, is there. Remember that halogens, those are any of the atoms in group 7A, so fluorine, chlorine, bromine, or iodine. If you check out a periodic table, if you don't have one, you might pause the video and pull one up on the internet. You'll see in group 7A on the right side of the periodic table, you'll have those halogens. Those are counted as branches. And so here, the most important thing is going to be this OH. That's going to be our functional group that defines the behavior of the molecule. So the longest chain I can find that includes that is 1, 2, 3, 4, 5, 6 carbons long. I'm going to circle that. That's going to be my parent chain. I'm going to circle it, include the functional group in that backbone so that it stands out from the other things, which are going to be named as branches. Okay, well, if you have 6 carbons in your backbone, the prefix for 6 carbons is hex. And so here, this will be, the name of the backbone here is hex. That's the first part of it. The second thing, the infix asks us to look at bonding. What is the bonding like? Do we have all single bonds, any double or triple bonds? And so if we look at this, we see that in this backbone there are only single bonds. And so the infix will be AN. Remember, you can remember these infixes because they follow the vowels. The first vowel is A, the second vowel is E, the third vowel is I. Over time that got changed to a Y. So A, E, I, O, U. And that can help you to remember those infixes there. So if you have all single bonds, that's the first vowel, A, and then you just have the N. And then for the suffix, that's where we represent the functional group that we have. And here we have an alcohol. So the suffix will be OL, as we've seen. Okay, so we have hexanol. Now that's not the full name for the backbone, because we have to say where the alcohol, where the OH is attaching. And you could see that it's coming off of carbon number 2. You could picture it coming off of the end or coming further in the middle. And so this would all give you different molecules that would have different shapes, and so would fit into different pockets in living things, and so would behave differently and cause different behavior. So we want to say where the OH is attached in this particular molecule, and here it is attached to carbon number 2. Oops. Carbon number 2. So I'm going to put that 2 here. Remember that always between numbers and letters goes a dash. So the name for the backbone will be 2-hexanol. Now you might also see this written in a different way. Now that you're starting to see these functional groups, I want to show you this other way of putting numbers in to the name of the backbone. And that is to put the number that tells you where the functional group is right in front of the functional group. So if you prefer, you could write this as hex and then right in front, now remember always between numbers and letters goes a dash, but right in front of the suffix, which is telling you what functional group you have, that's where you can put the number that tells you where that functional group attaches. So these are both completely correct ways to name the backbone here. 2-hexanol or hexan 2-ol. Okay, so much for the backbone. Now, let's think about the branches. First, the carbon branch. We have a carbon branch coming off of carbon number 2. So I'll put the 2 there. Always between numbers and letters goes a dash. In that carbon branch, there's only one carbon. The prefix for one carbon is meth. So we'll have meth. And because it's a branch, immediately after the prefix, you have a YL. So YL. So that's going to be, this branch here will be 2-methyl. That's the name for that. we have two other branches. They're both coming off of carbon number 5. So 5, always between numbers and letters goes a dash. And these are bromines. Now, bromine is one of the halogens. It's in group 7A. So again, if you look at the right of the periodic table in group 7A, you have fluorine, chlorine, bromine, and iodine. And when these are branches, you take the first syllable, so fluor, chlor, brom, and iod, and then you just add an O. So fluoro, chloro, bromo, iodo. So here we have bromines, so it will be bromo and bromo. So each of these are separate branches. This is one branch, and the name for that is 5-bromo. This is another branch, and the name for that is also 5-bromo. Okay. Now, whenever you have more than one of the same type of branch, so these are both bromo branches, you can squish them together. So you put the numbers together, separated by commas. So 5, 5, always between numbers and letters goes a dash. And then you want to use a prefix that says how many branches you've squished together. Here we've squished 1, 2 together, so we'll use the prefix di. And then we have the name for the branch, so bromo. So together, these two branches would be called 5,5-dibromo. And we've squished them together like this because they're both the same type of branch. They're both bromo branches. Notice that you can still squish them together if they have different numbers. They just have to be the same type of branch. Okay, so we sort of have three puzzle pieces here. We have 2-methyl, that's 1. We have 5,5-dibromo, that's 2. And then we have our backbone name. I'm just going to use 2-hexanol for this purpose, but you could just as well use hexane 2-ol. So we have to put all of these together. The backbone name always comes last. The branch names you put in alphabetical order, but when you alphabetize them, you don't count the prefix. So you're really comparing the M and the B. Because B comes first in the alphabet, the branch that starts with a B will come first in the name. So we'll have 5,5-dibromo, always between letters and numbers goes a dash. Then 2-methyl, always between letters and numbers goes a dash. And then 2-hexanol. So the beautiful lyrical name for this delightful compound is 5,5-dibromo 2-methyl 2-hexanol. Okay, next, let us go on to B. Now, with B, we're seeing a new type of bond that you would have seen in Organic Chemistry 1, but just to review, if you have most bonds are written just with a straight line. There are two other ways to draw a bond. It could be a solid wedge, or you could have a dashed wedge. If you have a straight line, just a regular line, that means that the bond is in the plane. So it's not coming out at you, it's not going away from you, it's in the same plane as the paper or the screen or the blackboard that you're looking at. And then a solid wedge means it's coming out at you. And a dashed wedge means that the bond is going away from you. And these are important because these three-dimensional arrangements of things determine what type of pockets things can fit into. They tell you about their three-dimensional shape. Now, it's especially important when you have what are called chiral centers. If you remember, if an atom is bonded to 4 different things, and really it doesn't have to be an atom, anything in the universe that has 4 different sides comes in 2 versions, a left-handed version and a right-handed version. And those 2 versions are, because they're like your hands, they come from the Greek word for hand, which is chir, and so they're called chiral. So to unpack that just a little bit more for a second, if you look at your hand, you'll notice that it has 4 sides, a back, a palm, a pinky, and a thumb side. And like anything else in the universe that has 4 different sides, it comes in 2 versions, a left-hand and a right-handed version. And if you ever try to put your right hand into a left-handed glove, you'll see how different those two versions are and the significance of being able to tell the difference between them. So just like your hand has 4 different sides, comes in 2 versions, and the right-handed version won't fit into a left-handed glove, so likewise, if an atom is bonded to 4 different groups, then it will also come in 2 versions, a left-handed version and a right-handed version. And those will fit into enzyme pockets differently. A right-handed molecule won't fit into a left-handed enzyme pocket, and vice versa. Just like your hand wouldn't fit into, or right hand wouldn't fit into a left-handed glove. And so whenever you have these chiral centers, you want to tell someone whether you have the right or left-handed version so that they'll be able to predict whether it will fit into these enzyme pockets that may help cure a disease or not. Now, if it's a right-handed version, then it's called the R version, and if it's the left-handed version, then it's called the S version. These are really coming from the words for right and left, the Latin words. So the word for right in Latin is rectus, and the word for left in Latin is sinister. And so these are just telling you of the right-handed or the left-handed version of these atoms. Okay, now there was a step-by-step method for determining whether a chiral center was R or S, and you learned that in Organic Chemistry 1. And if you want an in-depth review of that, I strongly encourage you to watch the video for that in the review playlist from the Organic Chemistry 1 class. So I'm going to assume that you've already seen that you've already learned this. You should have had a significant amount of practice with this in Organic Chemistry 1, so here we're just going to use these rules to assign the RS configuration to the chiral centers that we have. Okay, so with those things explored a little bit, let's try to name this. The first step, like before, is to try to find the backbone. Remember, the backbone is the longest carbon chain you can find without going backwards or lifting up your pencil. And it has to include the functional group. So here it has to include that OH, that alcohol. Okay, well, it's carbon 1, 2, 3, 4, 5. The longest carbon chain I can find without going backwards or lifting up my pencil is 5 carbons long. The prefix for 5 carbons is pent, and so the prefix for this backbone name will be pent. If you look at the bonding to try to figure out the infix, you'll notice that it's all single bonds. So it's all single bonds in that backbone name. And so the infix for all single bonds is AN. Finally, we have an alcohol here. Oops. We've got this alcohol and the OH, and the suffix for an alcohol is OL. So we'll add that OL there. So it's pentanol. It's not just any pentanol, though. We have to say where the OH is attaching, and you can see that the OH is attaching to carbon number 1. So I'm going to put 1, always between numbers and letters goes a dash. So the name for this compound could be 1-pentanol. Another way you can write it is you can put the number right in front of the suffix, so you could have pentan. Always between numbers and letters goes a dash, and so 1, I'll just make that an explicit 1 so it doesn't look like an L, 1, and then all, OL, for the suffix. So either of those are correct names for that backbone, 1-pentanol or pentan 1-all. Okay, now that we've named the backbones, let's name each of the branches. We have branches on carbon number 2, on carbon number 3, and on carbon number 4. So we'll write those locants, those locations down with dashes after them, because always between numbers and letters goes a dash. Now in this first one, there's only 1 carbon there. The prefix for 1 carbon is meth, and so that will be meth. Because it's a branch, immediately after the meth comes YL. Okay, how about 3? This one has only 1 carbon there. The prefix for 1 carbon is meth. And because it's a branch, immediately after that prefix will come the YL. On carbon number 4, we have also just 1 carbon. And so the prefix for that is meth. And because it is a branch, immediately after that prefix will come the YL. So notice that we have 3 of the same type of branch. All 3 of these are methyl branches. And so we can smush them together. We'll put the numbers together in ascending order, separated by commas. So 2, 3, 4. Always between numbers and letters goes a dash. Now we have to say how many branches we're smushing together. We do that by using a prefix. And here we've smushed 1, 2, 3. So the prefix for 3 is tri. And then we have to say what type of branch we're smushing together. These are all methyl branches. So the name for those 3 branches all together are 2,3,4 trimethyl. Okay, now we know the backbone name always comes last, and you could use either of these backbones. I'm going to use the one on top. So 1-pentanol, but either of them would be completely correct. And then you put the branch names in front. Always between numbers and letters goes a dash. So you might think that this would be the name of the compound, 2,3,4 trimethyl 1-pentanol. And it's certainly correct. Each of those pieces needs to be there. But this is still missing information. Anytime a compound gives you 3-dimensional information about the bonds, like they do here, it's very likely that you have a chiral center. So let's investigate and see if we really do have chiral centers where we have these 3-dimensional bonds. So let's check out, see these one at a time. I'm going to look at this left one first. Is that bonded to 4 different things? And you think globally when you do this. So to the left, you have, and you might remember the name of this group would be called an isopropyl group. If not, if that sounds foreign, that will come back, the isopropyl groups, and other common names for branches. And so if those sound unfamiliar, this is another time I would recommend for you to stop the video, pause, go back and watch that video. There's one in the playlist to review for Organic Chemistry 1 on branches, common names for branches. Okay, so that's one group. Another group, we have a methyl group on top, and then third, we have this weird branch over here with the OH, so that's 3 different things. In order to have a chiral center, though, you have to be bonded to 4 different things. So maybe that's not a chiral center, except that there is a 4th thing there. It is an implied hydrogen. Remember that in these skeletal structures, the hydrogens are implied, they're not drawn, because if they're drawn, they're messy and distracting. There are so many of them, they bristle off of carbon chains like bristles off of a toothbrush, and so if you write them all in, the compound can look unnecessarily complicated, so they're implied rather than explicit. Now, we have a hydrogen bonded here, and the way that we know is because only 3 bonds are drawn, 1, 2, 3, and there is no formal charge. There's no charge on the carbon. Now, in order for carbon not to have any charge, it has to have 4 bonds. Okay, so we know that a hydrogen has to be here. But is the bond going to be a straight line, a solid wedge, or a dashed wedge? For that, recall that carbon, when it has 4 bonds, is tetrahedral. And any tetrahedral molecule, when you have 2 bonds in the plane, the third bond, one of the bonds will be coming out at you, and the other one will be going away. So anytime you have a tetrahedral atom, and you have 2 bonds in the plane, so notice like these 2 bonds, oops. These 2 bonds are in the plane, just like these 2. You'll have one coming out at you, like this one here, and the other one has to be going away. And that's what the hydrogen is. So to show that that's going away, we'll have this dashed line there. And that is our 4th group. That is the group that tells us, yeah, that carbon is bonded to 4 different things. Therefore, like your hand that has 4 different sides, it is chiral. Okay, anytime you have a chiral center, you have to say whether that chiral center is right-handed, the right-hand version, or the left-hand version of itself, R or S. Now the first step to do that, we're going to follow these CIP rules. They're called the Kahn-Ingold-Prelog rules. And those are the last names of a few scientists who came up with them. The first thing is to prioritize all the groups, assign a priority to each of the 4 atoms bonded to the chiral center. And you do that by using the atomic number. Remember that the atomic number is the number at the top of each box on the periodic table. So I'll use this bright green here for this. Here we have carbon, carbon, and carbon. Those all have an atomic number of 6, and so they all tie. We'll talk about what to do. We'll see what to do in that case in just a second. Hydrogen has an atomic number of 1. That's very low. That's the lowest atomic number on the periodic table. And so this gets the lowest priority, a priority of 4. So notice how the lowest atomic number gets the priority of 4, the highest atomic number will get the priority of 1. Okay, because these other 3 tie, we need to make a table for each one. So I'll make a table for the carbon at the bottom right, for the carbon at the bottom left, and for the carbon at the top. Now in that table, I'm going to list the 3 things that that atom is bonded to, going away from the chiral center. And I'm going to list those things in order of descending atomic number. So first, this one on the right. It's bonded to a carbon, and, going away, a hydrogen. I'm going to put the 2 carbons first because they have a higher atomic number, and then at the bottom, I'll put the hydrogen. Okay, how about the one on the left? That's bonded to a carbon, and an invisible hydrogen, an implied hydrogen. So that will be carbon, carbon, and hydrogen. And the one at the top is bonded to 3 implied hydrogens. So because those all have the same atomic number, it doesn't matter what order you put those in. Once you have your tables, compare each table, but only one row at a time. Only if the rows tie would you go to the second row. You could see how, while these 2 tie, they're both carbons, the one on the top has a hydrogen, and that has a lower atomic number. So we know that this is going to have a priority of 3. It's going to have the next lowest priority. Okay, so now to choose between these other 2. And again, this is all stuff that you would have seen from Organic Chemistry 1, and if you want a more in-depth review of this applied to more molecules, I encourage you to see the review videos that I have online. If you go to the second row, those rows also tie, so then you go to the third row and those tie again. In other words, these 2 carbons are equally tied. So you want to go to the next carbon in the chain. The next one that's bonded to the stuff with the highest atomic numbers. Now here we have 2 methyl groups, so those are the same. It doesn't matter which one we go to. So that's the new thing we're going to compare on the left. And on the right, I have a methyl group at the bottom, and sort of to the right I have a methyl group but with an OH on it. The oxygen has a higher atomic number, and so that's the direction we're going to go in, and that's the atom we're going to compare in our new table. So I'll make a table for the carbon on the left and a table for the carbon on the right. The carbon on the left is bonded to 3 implied hydrogens. The carbon on the right is bonded to an oxygen and 2 implied hydrogens. The oxygen goes first because it has the highest atomic number, and then the 2 implied hydrogens. Notice when I do this, I always go away from the chiral center. You never go back, right? I'm never going back in this direction. I'm only going away. Okay, so now that we have these 2, we can compare. We compare these one row at a time. If you look at just the top row, you'll see that this carbon on the right is bonded to an oxygen, and that has a higher atomic number than the one on the left. That means that that group gets a higher priority. It has the highest priority of 1, and this other one will have a priority of 2. So we assign priorities to the 4 different groups bonded to the chiral center based on their atomic numbers. Next, we need to make sure that 4 is pointing away. Luckily it is here. We'll see what we would do if it's not, when that comes up. Okay, finally, ignore 4 and go from 1 to 2 to 3. If you go clockwise, like we are here, then it's the right-handed version of the molecule. You can remember that because as you go from the top to the bottom of an R, you go clockwise. If it were counterclockwise, then it would be the left-handed version. So here, it's going to be the R, or right-handed version. Now remember where this was in our original molecule. We numbered the molecule from right to left. So this was on carbon number 3. So we're going to have 3 R. Okay. Next, there's one other place that could be a chiral center, and the reason why I think it could be a chiral center, the reason what should stand out and make you think that it should be a chiral center, is the fact that they gave us these three-dimensional information for the bond, and that's right here on what was carbon number 2. So the question is that a chiral center? Let's see, is it bonded to 4 different things? It has a methyl group. It has a methyl group. It has a little methyl with an OH on it. It has a sort of complicated branch here. That's only 3 different things. But remember, this carbon doesn't have a charge, and so it has to have 4 bonds. The 4th bond is to an implied hydrogen, and that implied hydrogen must be going away, just like last time, because this carbon is tetrahedral, and 2 bonds are in the plane, and 1 is coming out, so this last one has to be going away. Okay, well that is our 4th group. We have 4 different things bonded to that atom, and just like your hand, which has 4 different sides, that will come in 2 versions. It will be handed or chiral. So we have to say what type of hand we have here. Now I'm going to do this kind of quickly, first because it's a review from Organic Chemistry 1, and second because we took a little bit of time to walk through this in more detail in the last example. So the first step in the CIP rules to assign the priorities, R and S, is to assign priorities based on the atomic number. So here we have a carbon, those 3 tie, and then we have a hydrogen. Hydrogen has an atomic number of 1, which is the lowest on the periodic table, so it will have the lowest priority, a priority of 4. For the other carbons, we're going to make tables to try to break the tie. So I'm going to make a table for the one at the right, for one at the bottom, and for the one at the left. Now we're going to see what 3 things these carbons are bonded to going away from the chiral center. So the one on the right is bonded to an oxygen and 2 hydrogens. I'm going to put those in order of descending atomic number in this table. So the oxygen comes first, because it has the highest atomic number, and then the 2 hydrogens will come next. Okay, so much for the one on the right. Next, the one at the bottom. This is bonded to 3 hydrogens. And notice how I'm only going away from the chiral center. I'm not going towards it. So I can write hydrogen, hydrogen, and hydrogen. Finally, the carbon on the left is bonded to a carbon, and an implied hydrogen. And that would actually be going away. So I'm going to put the 2 carbons first, because those have a higher atomic number than the hydrogen, which will come last. So those are our 3 tables. And now we compare these tables, and we do that just 1 row at a time. Only if the rows tie, the top row ties, would we go to this, look at the 2nd or the 3rd row. So we have oxygen, carbon, and hydrogen. Here, there are no ties. The oxygen has the highest atomic number, and so that group gets the highest priority, a priority of 1. The carbon has the next highest atomic number, and so that group gets the next highest priority, a priority of 2. And finally, hydrogen has the lowest of these, and so that group will have a priority of 3. So we figured out the priorities for each of those branches bonded to the chiral center here. Now we need to make sure that 4 is pointing away. If it's not, we'll discuss that when it comes up. There's enough to practice here already. And then we're going to ignore 4 because it's going away. We're just going to go from 1 to 2 to 3. And notice that when we do that, we go counterclockwise. If it's counterclockwise, then it's the left-handed version. You can remember that, and so it's S. You can remember that because if you go from the top to the bottom of an S, you have to go counterclockwise first. Okay, so that chiral center is the left-handed version of itself. And so, remember where that is in the grand scheme of things. That was on carbon 2. And so on carbon 2, you will have this S. Now, this three-dimensional arrangement of stuff that changes how the molecule fits into pockets and receptor sites, that three-dimensional arrangement of stuff is called stereochemistry. Stereochemistry is the three-dimensional arrangement of molecules. Stereochemistry always is put at the very beginning of the name. Now, when you list these R's and S's, you put them all in parentheses, separated by commas. So the stereochemistry for this molecule would be 2s3r, and we're going to put that in parentheses in front of everything else. Always between letters and numbers goes a dash. So the full name for this compound would be 2s3r234 trimethyl 1-pentanol. It's almost Shakespearean. And so that would be the name for that beautiful molecule. So I'm going to stop this video here just to avoid making these excessively long. We'll continue with C in the next video.